Hi everyone, and welcome to another mini course at Physics Latam. Today we are very happy and honored to have Yukinobu Toda giving a talk and a series of lectures on Gopakumar-Vafa Invariants. He is a mathematician known for his contributions in understanding the geometry of derived categories and has contributed to the study of Bridgeland stability conditions, which is an area important in algebraic geometry and also in string theory. His research also explored the Donaldson-Thomas invariants and their connection to moduli spaces of sheaves. He has held academic positions at the Kavli Institute for the Mathematics, Physics and Mathematics of the Universe at the University of Tokyo since 2008. In his research, he used the notion of stability conditions on the right categories to give application to the study of Donaldson-Thomas invariants and Gopakumar-Vafa invariants, as you will learn. In recent years, he has also interest in categorifications of Donaldson-Thomas invariants, which I don't know if he will cover, probably not, but it's also very interesting. Thank you very much for accepting the invitation, and please go ahead.
Okay, so thank you very much for the introduction, and also, thank you very much for inviting me to this lecture series. So I'm going to talk about Gopakumar-Vafa invariants from algebraic geometry point of view. So, so can I share the slide with the audience by?
Sure, definitely. I will post it also on the website so they can get it from there.
Yeah, I have sent the file of this slide from the chat. Okay, so the goal of this lecture series is that I'd like to explain about the notion of the Gopakumar-Vafa invariant. So these are some animated invariant curves on curvature threefolds. That is, so basically, I want to define like invariant like this. So G is the genus and beta is some homology class of curves. And these are the fundamental invariants of curves on curvature threefolds. And there are several ways to define it, either from Gromov invariants or Donaldson-Thomas invariants. And but there's another definition following the original approach by Gopakumar-Vafa using some homology theory of the modular space of so-called D2 branes. And mathematical foundation was proposed by my work with Tabeshimovic several years ago. But the issue of this construction is that it requires lots of techniques in algebraic geometry, especially some abstract notions of like sheaves, derived categories, or so on. So the goal of this lecture is that to explain these technical concepts of algebraic geometry, so that the like physics people can also access this invariant. But yes, today I will talk about very quick introduction of algebraic geometry. And so many of the people may know about this, but so this is just from the introduction of algebraic geometry, which gives a bridge between the physics motivation and also the mathematical motivations. So yes, let's discuss what the algebraic varieties. So basically, these are some space which is defined by some finite set of polynomial equations. For example, so like in high school, you learn like line or parabola. So given by these equations, say for example, like you have this line, and also parabola looks like this. But the last one is more difficult. So this is elliptic, and so in here you can write something like this. But this is the shape of the algebraic varieties in the real coefficient. And but in general, it is better to consider the complex to work with complex number field. To see this, let's also consider another example that for each real number, let's consider this algebraic variety. And so the shape of this variety is, in fact, depends on the choice of the additional parameter A. So that if the A is positive, then this is like ellipse For example, A equal 1, this is just a circle. And when A equals 0, so then this is part becomes 0, so that the sorry, you get only the 2 lines. And when A is negative, then you get the hyperbola that looks like this. So by looking at the case of A is positive and A is negative, you get quite defined shape of the varieties that are defined over the real numbers. And this happens because these varieties are defined over the real numbers, so that the it is not algebraically equal to field. So instead, he consider the solution space over the complex number field. So in the previous slide, the x and y are real numbers, but let's consider the case where x and y are complex numbers. So then, regardless of the value of a, non-zero a, this space is in fact isomorphic to the affine line minus 1 point, that is C star. And topologically, so this is the topologically, so this is the sphere minus 2 points. So if you compactify it, then you get the same space, that is one-dimensional projective space. So in fact, so you can directly construct the isomorphism between this the C star and also this V prime by this by this map. The point here is that when A is negative, when A is non-zero, then the square root of A always exists. So this is a defined point of either you consider the real number or complex numbers. So from this viewpoint, it is quite natural to consider the algebraic varieties of a complex number field. And similarly, if we consider the solution space of this equation over the complex number field. So then, so this is also an example of the empty curve over the complex numbers, and this is so homomorphic to the torus, but with 1 point deleted. So in particular, if you compactify it, then you get the two-dimensional torus. So in this method, this is essentially defined from the previous variety VA prime. In the previous VA prime, if you compactify it, you get the simply connected space. But here, so you get a non-simply connected space. So from these examples, it is more natural to consider the algebraic varieties over complex number field. So that is algebraic closed field. So one of the basic problems in algebraic geometry is that to understand the relationship between the defining polynomials and the associated solution space over the complex number field. So this is the basic question in algebraic geometry. So here is a quite general definition of affine algebraic varieties. So the previous examples are the examples of affine algebraic varieties, and given finite set of polynomials. So then we can consider the usual solution space, that is the set of points in Cn, so that these equations are zero for each polynomial. And it is called affine algebraic varieties. So this is a geometric space, but it is important to notice that there is a one-to-one correspondence between each point of this X and also the maximal idea of this commutative link. So this observation is a link between the geometry and algebra. So because maximal idea is an algebraic notion. And the correspondence is that for each point in X, if you are given A1 to AN satisfying these equations, so then if these satisfy these equations, then this ideal contains this ideal, so it naturally associates a maximal ideal of this ring R. And conversely, if you every maximum ideal of this R is of this form, where A1 to AN lies in X. And sometimes algebraic variety have some singularities. So that is one of the defined point from the usual complex manifold theory. So, there are several definitions of singular or non-singular varieties, but one intuitive way to define it is that as a complex manifold, this is locally isomorphic to an open subset of this of the affine space. So in particular, there is a complex coordinate system at each point, so that the if the algebraic variety is not singular, we have some coordinate system like this. Say Z1, Z2. For example, let's consider this algebraic variety. So for each number, for each complex number A. So of course, when A is non-zero, so then this WA that's going to C star, this is because when A is non-zero, sorry, this is a misprint, so this is not C, so this is 0. When A is non-zero, then you can solve it y equals A over X. So the given X, then you can also recover Y. So in that case, WA is non-singular, but the when A equals 0, this is the union of the two lines, right, like this. And in that case, you cannot take the coordinate system at this point. So in this case, W0 is a singular point. So there are several types of other singularities. For example, like you can consider this kind of singularities, so like y squared equals x cubes. And also you consider two-dimensional singularities, x squared plus y squared plus t squared equals 1 equals 0. Then this is singular at the origin. Also, there is an important notion of the Zariski topology in algebraic varieties. For a given affine algebraic variety X, its classical topology is not necessarily a good one. This is because in algebraic geometry, we want the map or function to be only the polynomial functions or polynomial maps. For example, if we consider the exponential map from complex numbers to complex numbers. So then this is, of course, continuous function in the classical topology, but it is not a polynomial map. Of course, this can be written by 1 plus x squared plus in this way, so that this is not a polynomial map. And we'd like to exclude such map in algebraic geometry. And we want to exclude it as a continuous map. So then there is a topology called Zariski topology, which excludes this function as a continuous function. So this is defined by for each affine variety and also some polynomial. We set UF to be the set of point where fx is non-zero. So then this is then there is a topology on X whose open basis is given by these ones. So this topology is that each open subset is quite big. For example, when X equals just C, then the open subset is nothing but the either empty or C minus finite set. So this is because for each non-zero polynomial, there are only finite number of solutions, and each open subset is just the excluding this zero locus. In particular, each open subset is dense inside of this one. And we have also notion of the morphisms of affine algebraic varieties. Let's give another variety y given in this equation. So then, similarly to the function on affine variety, we want to have the map from one variety to another variety y, the map of this form, so that the h1 to h are some polynomial functions. And because each hi is a polynomial function, it is a continuous map in Zariski topology. And again, so this is also regarded as regarded in terms of some algebra. So yeah, so this point is also important in the scheme theory, which I explain later. But given this kind of function, this kind of map, then there are some natural link homomorphism from this link to this link by sending yi to hi. But so roughly speaking, so S is the set of functions on y, and R is a set of functions on x. And this map is like putting back the function on y to the function on x. But in order to make it well defined, we need to assume that there's no nilpotent element. And the well-definedness of this link homomorphism is a consequence of the so-called Hilbert-Newstein set. So yes, we have this kind of notion of the map of affine varieties. And in general, algebraic varieties can be defined by gluing affine algebraic varieties. So by definition, topological space is called algebraic variety if it is covered by some finite open subset, and also affine algebraic varieties Vi together with homomorphism Yi. So here it is important to take the Zariski topology, such that for any affine open subset, we have this transition function. So this is a morphism of algebraic variety. So roughly speaking, so this means that the algebraic variety is a gluing of affine varieties, where these gluings are given by polynomial function. So this is similar to the concept of usual manifold, where in the manifold theory, we take a gluing of open subset of the Euclid space. And instead of considering Euclid space, we consider affine algebraic varieties as the local data. So this is a basic example for the projective space. Let's take the quotient of Cn plus 1 minus 0 by the one-dimensional complex torus by the usual action of C star onto Cn plus 1. So this action is free. And you can take its quotient and to get the space. And this is a basic example of algebraic varieties. So in fact, it is covered by open subset Ui, where each Ui is the locus where the Yi is non-zero. And this is isomorphic to Cn by this correspondence. That is for each Y0 to Yn, where Yi is non-zero, and if you take the quotient by star and Yi is non-zero. So then this correspondence becomes isomorphic. Conversely, given point in Cn, you can associate a point where where Yi, you can, for example, the Z0 to Zn or to like 0 to 1 to Zn. So where this is the ith coordinate. And for each point in Cn, I denote this corresponding point by this notation. And similarly, we can define the set of polynomial equations or inside of this projective space. So let's take homogeneous polynomials Fy, where Fi is 1 to n. So homogeneous means that the degree of each monomial is depends only on I. So then the set of equations, so this is very defined, and this is algebraic variety. So similarly, as I said, so Pn can be covered by finite open subset, where each open part is the usual affine space. And so this is the open subset of Pn, where yi is non-zero. And the intersection of this ui and x is given by this way. And this is also affine algebraic varieties. And algebraic variety defined in this way is called complex projective variety. And open subset of such variety is called quasi-projective variety. So it is important to classify algebraic variety. So this is a very classical subject. And it is called, algebraic variety is called curve if the dimension of this variety is one-dimensional. So usually we consider the complex number field. So curve means that real two-dimensional. So this looks like real surface. And for smooth projective curve, its genus is defined to be the half of the dimension of H1. So this is in fact in integer. So this number is always divisible by 2. And this xh is the topological space associated with the classical topology. So not the Zariski topology in this definition. So this is a classical classification of algebraic curves. So for smooth projective curve of a complex number field, it can be classified by genus, at least topologically. So when the genus is 0, this is isomorphic to P1. So this is topologically, so this is just the sphere. And when genus equals 1, so in this case, this is known to be a cubic curve inside P2. And this xh, so this is homomorphic to the torus. And when genus is bigger than or equal to 2, so this is like called general type. And so this is also looks like some donut type surface, but the whole may be bigger than or equal to 2. So this is a rough classification of algebraic varieties. And so one of the important goals of algebraic geometry is to extend it to higher dimensional. So let's consider examples of curves. As I said, so if you have the homogeneous polynomial, then there is associated algebraic varieties, projective variety. So in particular, if you give one single polynomial, then the set of zero locus of this function is algebraic curve inside of P2. And it is somehow exercise of computing the genus of this curve X, and this is known to be this one. For example, you can look at Hart's-Horn textbook to derive this formula. And in particular, when the degree of this curve is bigger than less than or equal to 2, then genus is 0. And the X is isomorphic to P1. And when d equals 3, this is cubic curve inside P2. And as I said, so this is elliptic curve. However, when the degree is bigger than or equal to 4, then the genus is bigger than or equal to 3, and it is of the general type. So in particular, so there is no genus 2 curve inside PP2, and you can find it only inside PP3. So then we can define very important class of varieties called Calabiar varieties. Yeah, there are several ways to define Calabiar, but here I employ this definition. So let's take a smooth complex projective variety X. So then you can regard it also as a complex manifold. So you can consider it a homomorphic vector bundle. Sorry, this is homomorphic tangent bundle. So this means that for each point, the fiber of this bundle is given just in this way. So these are the vector field at each point, this one. So then there is so-called canonical line bundle of this variety. So this is just taking the top wedge power of the dual of this tangent bundle. So this is a very important line bundle on algebraic varieties. And the algebraic variety is called Calabiar in some broad sense, if this is a trivial line bundle. Another way to say is that there is a no-fair vanishing global homomorphic N4, where N is a dimension of this variety X. So the one-dimensional case is that it is Calabiar if and only if X is elliptic curve. That is, the genus of X is just one. So yes. So as I said, so there are three classifications that G is 0, G equal 1, and G is bigger than or equal to 2. So in this classification is also has to do with the some size of the canonical boundary. So the G equal 1 case is where omega is 0. And G equals 0, so this is the case where the X is PP1, and in this case, omega minus 1 is positive, or omega is negative, and omega is positive. Okay. And in fact, in the G equal 1 case, so as I said, this is a cubic curve, but there is another way to describe it as a complex torus. That is, so this is also a classical well-known fact that each elliptic curve can be described as this complex torus. There for some complex number with positive imaginary part. So then there is a no-fair vanishing homomorphic one form on this on the affine space, on affine line. And this is invariant under this translation actions. So it descends to a global no-fair vanishing homomorphic one form on X. So in this way, so this elliptic curve is an example of the Calabiar varieties. And in fact, this is if the curve is Calabiar, then it must be elliptic curve. So elliptic curves play very important roles in several branches of mathematics and also mathematical physics, and also algebraic number theory or representation theory or so on. So there are several other examples of Calabiar varieties from complete intersections. So let's take homogeneous polynomials, f1 to fk, so that each degree of fy is di. So then we can take x to be the intersection of the locus of each f1 to fk. So this is a projective variety. But if let's assume that this is also smooth and also complete intersection, that is the dimension of x is the same as the dimension of n minus the number of the polynomials. So in general, the algebraic variety may not be complete intersection. So this is quite restrictive class of varieties. But if you assume this, then I note it x equal d1 to dk, and it is possible to calculate the canonical boundary of this one. So I will explain this notation later, but the important point is that the definition of the Calabi-Yau is omega x is trivial. So this is checked just by the numerical condition of d1 to dk. That is, if d1 plus dk, the sum of d1 to dk is equal to n plus 1, then this is Calabi-Yau. In particular, if you take a generic polynomial of each degree di, satisfying these equations, then for generic choice of polynomial, then this is a complete intersection, so that it becomes the Calabi-Yau. Of course, when n equals 2, so this is the case where d1 equals 3, so that it is elliptic curve. So then we have also another classification of Calabi-Yau varieties in two-dimensional case. A smooth variety is called a surface if the dimension of x equals 2. So this is a complex surface, so real dimension is 4-dimensional. And this is also a classical fact that the smooth projective surface, it is Calabi-Yau if and only if it is either KC surface or Abelian surface. In the case of KC surface, then the variety with classical topology is homeomorphic to the. So this notation is that in the previous slide that so this is f equals 0 where degree f is 4. So this is the example of the KC surface, and in particular, it is simply connected. So this is one classification of the Calabi-Yau surface, and another classification is that Abelian surface. So this is, for example, so if you take the product of elliptic curve, then this is example of Abelian surface. And in this case, the topological, so this is homeomorphic to the two-dimensional complex torus, that is the self-product of S1. So in this way, we have only two topological types of Calabi-Yau surface. And however, in the higher dimensional case, like the three-dimensional case, it is not known whether we have only finite number of such Calabi-Yau varieties. So so Calabi-Yau seafold is most important and interesting case for us because we are eventually going to the curves inside Calabi-Yau seafold. Again, so a smooth projective variety is called Calabi-Yau seafold if it is yes, of course, complex three-dimensional and Calabi-Yau. For example, this quintic seafold. So this is the locus of the degree 5 polynomial equation. So this is one of the important example of the Calabi-Yau seafold. And also we have also other complete intersection Calabi-Yau seafolds. That is, so as I said, so the equation for the complete intersection to be Calabi-Yau is that like d1 plus 2dk equals to n plus 1, and n is the dimension of the ambient projective space. So for example, in this case, 2 plus 4 equals 6, 3 plus 3 equals 6, and so on. So in this way, so these are the only examples of complete intersection Calabi-Yau seafolds. And the Abelian seafold case is that we also have like for example product of the three elliptic curves. So these are also example of Calabi-Yau seafold in the broad sense. And the topological, so this is homeomorphic to the 6 times product of S1. Also, we have the product type that X is a product of KC surface and also elliptic curve. Again, the KC surface has trivial canonical boundary, and it has also trivial canonical bundle, so its product also has a trivial canonical bundle. So we have also, we have four, now these kinds of topological types of Calabrian seaports, but it is not yet known whether we have only finite number of topological types. So yes, eventually we are interested in curves inside Calabrian seaport. That is, so let's take X to be Calabrian seaport, like a quintic seaport, and also we want to consider curves with fixed genus and also the degree beta. Like the beta lies in Hxg. So for example, let's take a Fermat quintic threefold. So let's take this polynomial equation inside people. So because this is degree 5, this is Calabrian threefold. And also let's take xi satisfying this equation. So then associate each number, we have the rational curve given by this equation. So in fact, so this is a rational curve because if you given y, say y1 and y2, say y1 and y3. So then from this equation, you can recover y0 and also y2, and y5 is also 0. So in that case, so this curve C is parameterized by point in PP1. And in fact, so this is a curve inside of this X. And in fact, so this has genus 0. And also the H2XD of this quintic seafold is rank 1. And this is the most smallest one. So then the basic question is that why we want to consider curves inside Calabrian seafold. So this is the curves in Calabrian seafold interesting in several aspects. So for example, it is important in birational geometry, that is birational classification of algebraic varieties. In fact, so it is important to consider the curves inside the threefold, and there is so-called the comb curves in birational geometry. And analyzing this comb curves is important process of finding minimal model program in birational geometry. So yeah, starting from Mori, Kawamata, and its people developed this theory. But the curves in Calabrian seafolds are also important in mirror symmetry. So in string theory, so the universe looks like four-dimensional space-time, and also the very small Calabrian seafold. And also curves on Calabrian seafold correspond to world state or D-branes in string theory. So this is important. The Calabrian seafold and curves on them are very important both in math and physics. Again, so as I said, so the curves on varieties are important in birational geometry. So two varieties, x1, x2, so these are called birational if there exists Zariski dense open subset such that U1 and U2 are isomorphic. So this means that birational maps are almost isomorphic, but there are something no isomorphic things happened beyond this open subset. For example, one of the examples is so-called the blowing up. That is, for example, starting from a complex surface, we can take the blowing up of this variety to get another variety. After blowing up, so you get some P1 pairs. So outside of this locus, let's say x2 and x1. Outside of this locus, x2 and x1 are isomorphic, but they are not isomorphic as varieties. And the birational classification of algebraic varieties is, so this is one of the central topics in algebraic geometry. As I said, so there is so-called molecon that is spanned by the classes of curves inside of this H2, H6i. And the behavior or shape of this curves is very important in the in birational geometry. For example, there is a notion of the extremal ray in the curves, and if you find your extremal ray, then you can construct your x to some varieties, and the minimum model program is a step of each of continuing this process. And this is also important in mirror symmetry. So around 1990, Candelas and these physics people predict that the number of rational curves on quintic Calabi-Yau C-folds can be calculated through the mirror symmetry. So the key idea was that so there is also mirror manifold. So this is a quintic C-fold, and there is also another Calabi-Yau C-fold called mirror manifold, such that the number of rational curves on X is also equal to the some coefficient of some solution of the differential equations called Picard-Hooke's equations. And this Picard-Hooke's equation appears, the solution of the Picard-Hooke's equation appears as some period integrals over the mirror manifold. So this happens from the deformations of complex structures. So both sides are quite different kinds of mathematics, and it is surprising that the number of rational curves can be computed from some differential equations. And in fact, the physicists predict that the number of rational curves given in these numbers, and later mathematicians proved it, and also Giventhal mathematically proved these formulas predicted by physicists. So that was a very amazing story for mathematicians. But the question is that what is the meaning of the number of curves? So of course, if there is only a finite number of curves, then you can just count it. In the case of quintic C-fold, there is a so-called Clemens conjecture that is for a given degree d, and also the generic quintic C-fold. So then there are only finite number of rational curves C with given degree d. So this is still conjecture, and I think this is proven only up to these less than or equal to 11. But anyways, if you know Clemens conjecture, then you can define the number of rational curves just by taking the generic quintic C-fold and then count the number of curves. However, I think this is a quite special situation, and in general, if you consider a set of curves inside the Calabi-Yau C-fold, then usually so this is not finite, even if you pick some degree and genus. For example, let's take the product variety, that is KC surface product empty curve. So then, of course, for each point of this KC surface, there is an empty curve given by this one. Another way to say that, so there is a fibration from X to S, and each fiber gives a curve, genus 1 curve inside of this curve, inside of this X. So this means that we have a family of the curves on Calabi-Yau C-fold, and it is not clear what is the definition of number of curves a priori. But I will say later about the virtually the number of curves inside the Calabi-Yau C-fold zero-dimensional. That is, virtually it is regarded as only finite number of curves. So the idea of normative geometry is to get some virtual count of curves in Calabi seafold. So in this lecture series, the final goal is to introduce this invariant, which virtually counts genus G and also degree beta curves inside Calabi seafold X. And there are three approaches, and in fact, there are three definitions from Gromov-Fit invariants. So this is defined from the stable maps. Another way is that Panay-Thomas invariant, or also Donaldson-Thomas invariant, so which are known to be equivalent. But anyway, so there is a definition from this one, and in fact, the equivalence between the first and second definitions are now proven. So this is a consequence of the so-called Gromov-Fit DT correspondence, together with some sort of vanishing result from the symplectic geometry. So these are quite deep results. But my focus is that the last one. So yes. So geometrically, the first one is counting maps. That is, this is a map from some curve to Calabi seafold. The second one is that curves inside Calabi seafold together with some data of the point. So in some sense, both of the first one and the second one, so these are quite well defined and well behaved invariant, but nevertheless, they are not ideal curve counting invariant. In a sense that in the first Gromov-Fit invariant, this is not integer, but it is a rational number. In the second one, so this is integer, but it does not directly count curves, but it is rather data of curve together with point on the curve. So the last one is, so this should be the one which directly count curves. And this is defined from the moduli space of stable sheaves. And also using some cohomology theory of the moduli space of stable sheaves. And so in order to define the last one, I need some more concept of algebraic geometry and X schemes, sheaves, and so on. So yes, I'm not going to explain about schemes, but are there some questions? Okay, so then I will go to the introduction to scheme theory. So far I have considered only the varieties, but in order to define the Vafa invariants, we have to consider schemes rather than the varieties. So yes, let me explain why scheme theory is required. So let's consider two affine varieties. So x is given by y equals y minus x equals 0. So that is so this is of course set theoretical. So this is only one point. So this is y equals 0 and y minus x equals 0. So the set theoretical. So this is just a point, and y is, so this is y equals 0, and also this parabola, and so set theoretical this is also 0, and but of course you take the equation for x and y. So for x, so the equation is just this one. So this is a single point, but for y, so this is x squared equals 0. So if this is seen from this one. So y has a double solution. So we want to regard these set as defined spaces. Of course, you cannot distinguish as a topological space or affine varieties because they are anyway topologically isomorphic. So the key idea for scheme theory is that we want to use the link of functions. That is, the link of functions on X is given by this commutative algebra. So this is just complex numbers. And for Y, so if we take the quotient of these two equations, we get another link. Of course, Rx and Ry are not isomorphic. So the idea of the scheme theory is that to use the link of functions to distinguish these spaces. So here is the definition of affine scheme. So for a commutative ring R, the set spec R is defined by the set. This is defined by the set of prime ideals in R. For example, the spec Z is this is each prime ideal is either generated by prime number or just zero. So the set spec Z is given this way. Also, the spec of this two polynomial two variable polynomial ring is so either each prime ideal of this one is either of this type or this one or this one. So these are the maximum ideals. And G is the irreducible polynomial. And 0 is just 0. So geometrically, so each point corresponds to some affine some variety of C2. For each maximum ideal, so we have the associated point. And for each GXY, we have the associated variety. And for 0, so this is equal to C2. So in this way, so each point in spec R may be regarded as a certain subvariety, irreducible subvariety over the yes. For example, in this case, so this corresponds to the yes. Corresponds to subvariety over C2. And so this is a remark that for each for F1 to Fk, so these are polynomial. So then if we consider the usual affine variety given by this polynomial equation, so this is the set of points where F1 to Fk are 0. And as I told, so each point of this one corresponds to the maximal ideal. So if you take A1 to AN, so then there is associated maximal ideal. In this way, theoretically, the point in affine affine variety is included in the associated affine scheme. And similarly to the case of affine varieties, there is the so-called Zariski topology on spec R. That is, for each commutative ring R, so there is a topology on spec R whose open basis is given by this UF. So this is an analogy of the similar open subset in affine varieties. In affine varieties, so the UF was defined in this way. And this is the analogy of this open subset in the scheme theory. In fact, if P is given by maximal ideal, like xr minus a1 to xn minus an, so then this condition is equivalent to that if a1 to an is non-zero. In this way, so there is a topology on spec R called Zariski topology. And in this topology, it's a set of maximal ideals. So as I said, so this one corresponds to the point in affine varieties. So these maximal ideals correspond to the closed point with respect to this Zariski topology. The closed point means that the closure of this point is equal to this original point. So in fact, if you take no maximal ideal, then it is not a closed point. For example, in the case of like in the A1 case, so this is spec of X, and it contains 0, so this is called a generic point. And if you take the closure of this one, then this one is equal to A1 itself. So in particular, so this is not a closed point. So in this way, we have a topological space, spec R. But our purpose is that to distinguish the two spaces like this, for example, spec C and spec C over X square. So now C is a field, so the spec C is just the one element 0. And the spec C X over X square, so the only primary ideal of this ring is the ideal generated by X. Because if you take the quotient of this ring by X, then you get the C, which is field. So this means that this is in fact a maximal ideal. So topologically, both are homomorphic to one point. So as a topological space, we cannot distinguish these two spaces. So we need more structure on this topological space. And for this purpose, we need the notion of sheaves and shifts to distinguish these two spaces. So in order to explain about the shifts, I will talk about phase shift. So this is just assignment of each open subset to some Abelian group. So there are also several other versions. So for example, you can replace Abelian group with for example, vector space, or you can also replace it with some commutative algebra or so on. But so this is the sheaf of Abelian groups. And also together with restriction maps for each open subset, and satisfying some conditions that of course, V for view, then this restriction map must be identity. And also there is this transition loop for each chain of open subsets. Maybe one of the easiest example of sheaf is that a pair sheaf is that you can associate for each open subset the constant functions. So the constant function, so so this is just the yes, for each point, you get some number. But constant means that so this number does not depend on the choice of x. So in fact, so fu is in fact the choice of the number z. And of course, we take the restriction map to be identity. So this is a pair sheaf. But the pair sheaf is not a good one to consider. And because we don't have some sort of gluing property. The notion of sheaf is that the sheaf is a pair sheaf satisfying. Yes, the sheaf is a pair sheaf satisfying some sort of gluing properties. That is a pair sheaf F on topological space X is called a sheaf if we have these two conditions about gluing. That is for each open subset and it's open cover. So VI is the open cover of U, so that U is VI. So let's take U in this way, and let's say we have some open cover. So then, the first condition is that if S is FU, so this element is called a section over U, and if its restriction to each VI is 0 for all I, then S equals 0. That is, this means that if you have a section over U such that if it vanishes locally, then it globally vanishes. The second condition is about gluing. That is, if you are given SI on each VI, so let's suppose that we have this SI over here, such that they are same over the intersections. Let's say you have also section over here, section over here. So then there is some global section, that is. Then there is some section over U, which restricts to SI on each open chart VI. For example, in the previous slide, I considered the constant sheaf, that is, for each open subset, if U is a constant function U to Z. In fact, this is not a sheaf. This is because that if you take U to be the to disjoint union, and if you take if U1 and if U2, so this is in D and D, and let's take S1 and S2. But for the definition of the constant sheaf, if U is also D, so if S1 and S2 are different, then it cannot be glued to get to a global section FU. So instead, there is so-called sheafification of each pressheaf, which I will maybe explain later, that instead of constant sheaf, if we consider the locally constant functions, that is, so each f prime u is a function u to z, which are locally constant. So this means that if you take two different components, then it may take different values. In fact, so this is now equal to z of pi 0 u. So then this can be shown to be a sheaf. So in fact, in this case, if you take S1 and S2 to be defined 1, then from this definition, it can be good to get to a global section because we have this. In this case, this is rank 2 Abelian group. So we have some more notion of sheaves like the stalk and push forward and pull back. So the stalk is that for a sheaf f on x and each point, so its stalk is given by the limit of this one. That is, so we have this x and also x, and so each point of this stalk corresponds to is represented by some element in SU for some open subset. That is, so there is some open subset such that S is represented by this one. So roughly speaking, so the sheaf may be some sort of generalization of the notion of functions. So you can see that this is like a function. And the stock is something like a function which is defined in some neighborhood of this neighborhood of x, some function defined only as some neighborhood of x. There is also the notion of the push forward, that is for continuous map and the sheaf f. So f is rising here. So then its push forward is defined in this way that for each open subset U in Y, we take its pullback. This is again open subset in X, and then take its section. So in terms of the intuition that a sheaf is like a function, so then this push forward is like so the take some sort of integration of the function along the fibers of this map F. Or you can also say that so to say for each open subset, the function associated function over here is that the set of function over here is that so this is the function which defined over the pre-image of over U. And there is also the notion of pullback, and that requires the sheafification of the pre-sheaf. So I will, yeah. So this is explained in the later page of the slide. So then there is the notion of locally linked space. The pair of X or X for topological space X and its sheaf of links or X. So this pair is called locally linked space if each stock is a local link. For example, let's X be a infinity manifold, and let's take OXU to be the set of infinity functions on each open subset U. So this is in fact the locally linked space. That is, as I said, the sheaf is like the sheaf is like the set of functions over each open subset. And from this perspective, so OXX, each stock is the set of functions defined only in the neighborhood of X. So then we have the category of locally linked spaces, that is morphism between two local linked spaces is a continuous map together with a morphism of the series of links such that the indexed map on each stock takes the maximum ideal to the maximum ideal. Or this is just the homomorphism of the local links. So in this way, we can define the notion of locally linked space. And the scheme is a particular example of locally linked space. And in fact, we first define the affine schemes. So this is a scheme version of affine varieties. For commutative link R, as I said, so we have the notion of spec R. So this is a set of prime ideals of R together with Zariski topology. We have, so this is a topological space. And so there is some sheaf of links over this spec R, whose section over this open basis is given by this link. So you can regard it as some function on spec R. such that defined over UF. So in fact, the UF is something like the set of functions. Sorry, UF is the set of point where fx is non-zero. So this is like fx is non-zero. And if fx is non-zero, then this value makes sense. So in this way, so this ring can be understood as some function defined over this open subset. And similarly, we can consider its stalk, and each stalk is in fact the local ring, localization by this prime idea P. So this is also regarded as the set of functions which are defined near this point P. So then we have the locally linked space. And this is called the affine scheme. We can also define the notion of morphisms between affine schemes. That is, for each morphism of commutative rings. So then there is associated morphism of local linked spaces. So first, we have the map between topological spaces from spec R to spec S. So this is given by just sending each prime idea in R to its pullback. Yes. In fact, this pullback is also prime ideal. And we also have the induced map between the sheaf of functions. That is, so this is in fact induced by this map file. So then we can consider the category of affine schemes. So this is a very classical result by in Hudson that there is a natural functor from the category of commutative rings to the category of affine schemes. So as I said, for each commutative ring, so there is associated affine scheme. So this is the topological space is spec R. It consists of prime ideas of R. And there is a natural sheaf of commutative rings over this topological space, which makes this pair to be the locally linked space. And this pair is called affine scheme. And there is also some notion of morphism between affine schemes. And there is a correspondence that given R, then there is a corresponding affine scheme. And so opposite means that we have the opposite category. So I will later explain about some reminders of the categorical notions, but the opposite means that so if there is a link homomorphism, then we have the direction of the arrows are reversed. And conversely, if you are given a affine scheme that is X and OX, so then there is a corresponding commutative link by taking the global section of this sheaf of links over X. So in this way, so we can informally think that the theory of commutative links is more or less equivalent to the theory of affine schemes. But the left-hand side is, so this is right, algebraic notion. And the right-hand side is, so this is a geometric notion. So in this way, so the theory of affine schemes gives a correspondence between algebra theory and geometry theory. And also by recording that in the case of x is point, and y is spec of cx over x square. The topological space x and y are same, but the sheaf of rings on them are different. So on x, the sheaf of rings has, because they are only one point, so the sheaf of rings is equivalent to just the ring. But on the former, so this is just the one-dimensional vector space, and on y, so this is this cx over x square, which is so they are not isomorphic. So in particular, we can distinguish the two spaces as affine schemes. So similarly, we can define the schemes in general, similar to the varieties. So by definition, a locally linked space X or X is called a scheme if it is locally isomorphic to affine scheme. So this means that scheme is covered by affine open subschemes. So and each affine open subscheme is given by spec R or spec Ry. So similar to the case of varieties, so that we have some green functions which are defined by some element of the of some links, some element of the links. So in this way, one can say that a scheme is like a gluing of commutative rings. And if the number of each open subset is finite, and each y is finitely generated C algebra, that is like Cx1 to xk over f1 to fm. If each y is of this form, then this is called a finite type over complex numbers. So this is an example of schemes which happens from the construction of varieties. That is, let's take f1 to fk, so these are homogeneous polynomials. So then recall that we have the associated algebraic variety given by the f1 equals fk equals 0. So this is the usual projective variety. But there is also associated scheme corresponding to these data. That is the whose subset of closed point is given by this classical one. And in fact, each Pn is covered by open subset, and each UI was isomorphic to some an. And an corresponds to the spec of Cx1 to xn. And each polynomial, homogeneous polynomial gives some function on an. So that corresponds to this function. So then by taking the quotient of each fj, the ideal generated by each fj, so that this is nothing but this Ri. So then we have the associated scheme whose closed point is the set of points of this classical algebraic variety. So there is a classical result which connects the classical notion of varieties and also the scheme theory. So there is a free phase functor from the category of varieties to the category of schemes over complex number field. So as I said in the previous slide, if you are given the classical projective variety given by some set of homogeneous polynomials, then there is associated scheme given by using the same set of homogeneous polynomials. And this correspondence is that which send each affine variety f1 equal fk equals 0 to Cn to the spec of this reduced link. That is the quotient of this link R by the ideal given by this the so-called nilpotent element. That is, so this is the ideal given by the generated by this nilpotent element. So that is the, for example, when R equals cx over x squared, so then the corresponding rate is just the C. So in this correspondence, for example, spec of C lies in the image of this free-faced functor, but the spec of cx over x squared does not lie of this free-faced functor. So we can regard the classical varieties as the schemes which are reduced. Reduced means that for example, the spec R is called reduced. If R equals R let. So the point of the scheme theory is that we can also capture the non-reduced schemes, and which distinguish the scheme theory with the classical variety theory. Okay, so are there any questions? In the rest of the time of this first lecture, I give some reminders of some categories. So this is just the reminder of the notions which I will also use in the next lectures. So by definition, a category consists of the notion of the object and the homosets for each object A and B, such that there is a composition map satisfying this division, and also there is some identity element satisfying these natural conditions. So this is just the notion of the language in mathematics, and there are several examples like the category of sets, category of topological spaces, or so on. But it also generates the category of the like category of, it also generates the notion of algebra. For example, if you consider the category C with only one object, let's say this is just A. So then the only axiom is that we have this composition map and identity element. So this is nothing but the definition of the ring. So in this way, you can also regard category as the generalization of the notion of rings. So there are several examples of the categories for the category of sets, where each object consists of the usual set, and the home space is the maps from A to B. We have also the category of Abelian groups, where the objects are Abelian groups, and the home sets are the group homomorphisms. We also have the category of commutative rings, where objects are commutative rings, and home sets are ring home. We have the category of topological spaces, where objects are topological spaces, and home spaces are the continuous maps. So in this way, so we have several examples of categories. And we also have the notion of functors. For categories C1 and C2, a functor between these are just assignment of object in C2 for each object in C1, and also a map between the home sets, which preserves the compositions and identity. So this is also regarded as some generalization of the ring homomorphism. That is, for example, if you have the only one object for C1 and also for one object on C2, so then the giving the structure of the category is given corresponding to the ring structure on form of AA. And also, let's say we have the only one object B. So then we have the ring, and the functor is nothing but the ring homomorphism. And also, we have the several other notions, that is the opposite category, which are used in the affine scheme theory. That is the form of this opposite category is just the opposite of the home space. And a functor from the opposite category to the another category is called a contravariant functor from C1 to C2. Also, a functor F is called free face if this FAB is bijective, this one. So this is bijective for any AB. That is, if you only consider home space, then this is isomorphic. So this is the definition of the free face functor. And also, the functor F is called equivalence if it is free face and also essentially surjective. So if from this definition, you can say that each category is equivalent. In fact, the essential surjective means that for each object in C2, so there is some object in B, such that FB is isomorphic to A. But the free faithfulness implies that such a B is unique up to isomorphism. So you can construct an inverse functor from C2 to C1 by assigning for each A with some object B. Well, there are also several examples of functors. So for each integer, there is a functor from the, in fact, this is a contravariant functor from the topological space to the category of Abelian groups, which takes x to the hi xd. So this is the usual singular cohomology. And this is a contravariant functor because give x to y. So then we have the associated pullback map. So in this way, we have the functor from the category of topological space to the category of Abelian groups. Another example is that we can also regard sheaf as a play sheaf as a functor. That is, let's take op x to be the category of open subset. That is, the objects consist of open subset, and the morphisms are given by the open immersions. So the morphism is given by U1 included in U2. So let's recall that the play sheaf is assignment of each open subset to some Abelian group. And so if you are given open immersion, then we have the restriction map from FU2 to U1. So this one is something like restricting a function on U2 to a function on U1. And so this was the definition of the play sheaf, but this play sheaf is so this is nothing but a contravariant functor from this category of open subset to the category of Abelian groups. So there is also a notion of adjoint functors. That is, for a functor FC1 to C2, its right adjoint or left adjoint functors are defined by these conditions. That is, for the right adjoint functor, the condition is that form F1, F2 is isomorphic to form A1, FR, A2. So this is called right because from this equation, FR comes to the right. And similarly, so there is a notion of the left adjoint functor that is form A2, FA1 is isomorphic to home FF A1, A2. So these are very important notions in the category theory. Yeah, for example, for Abelian group M, let's consider the functors from the category of Abelian groups to Abelian groups. So the functor F is given by sending n to n tensor m. And G is given by sending n to home mn. So this is quite, yeah, so maybe elementary commutative elementary algebra theory that this functor F is a left adjoint functor of G, and G is a right adjoint functor of F. And then using the notion of adjoint functors, we can define the signification of the pervasive. That is for topological space X. So let sheaves X, pervasive X be the categories of the sheaves, pervasives on X, respectively. So then let's recall that pervasive was the functor from the category of subset to the category of Abelian groups. And the sheaf was the sheaf was a pervasive satisfying some gluing conditions. And there is a right adjoint factor of this reflexive functor called sheafification, and which makes each pervasive to a sheaf. So, for example, as I said, the pervasive of locally constant functions is not a sheaf. But if you take its sheafification, then it becomes a locally constant sheaf. And also the category of sheaves over topological space is Abelian category. That is, for any morphism, there is a kernel and cokernel. So this is a very important point about this Abelian category structure. That is, for a morphism of thieves, so the kernel is easy to describe. That is, its kernel is given by kernel as a pervasive. That is, for each open subset, the kernel is given by just the kernel of FU to GU. But the image is more complicated because if you just take its image, then in general, this is not a sheaf, but it is rather a pervasive. So in order to define the image as a sheaf, we have to take the sheafification of this, the naive definition of the image. So then take the cokernel of this one. So then you can also define the cokernel of this map F. So then by this definition of this Abelian category structure, a sequence of sheaves. So this is exact if and only if the induced sequence of stalks. So this is exact sequence of Abelian groups. But the important point is that so this is defined from the notion of exactness as a pervasive. In fact, if you have the exact sequence of sheaves, then the associated sequence of pervasives. So this is not necessarily exact. This is because we have to take sheafification for the definition of the cokernel. So this is why you have the notion of the cohomology theory for sheaves. In fact, so the next step, you have some cohomology of the sheaf. Sorry. H1U, F1 to H2U, F2, and so on. And also using the shiftification, we can also define the pullback, pullback. Yeah, push forward was also defined before that. For each map of the topological space, we have the usual notion of the push forward. So this is defined just considering the push forward as a pressure. But so in order to define its pullback, we have to take the shiftification of this pressure. That is for each open subset X. So we take this limit. So this is a pressure, and then take its shiftification to get the pullback. So the pullback is a bit more complicated, but nevertheless, the spoke of each F inverse G point is equal to GFX. So this is end of this first lecture, and in the next lecture, I will explain about coherent sheaves and also the derived category of coherent sheaves. And these are also important notions in defining the Donaldson-Thomas theory and also Gopakumar-Vafa theory. So yeah, today I stop here.